All right, let's start with the building block stuff and work our way up. Elements are the building blocks. They are what we see in the periodic table. Everybody's seen a periodic table, correct? I believe there's one in the book for you guys to have as a handout. Elements are single types of atoms. Atoms that are one type. If we have multiple atoms put together, they form what's called a molecule. If they're the same atom put together, they're what's referred to as an elemental molecule. So O2, 2 molecules of oxygen, that would be elemental molecule of oxygen. When we look at these building blocks of the body, we break it into 3 distinct categories based off of mass. How much happens to be there? Major, the most mass. Minor, less mass. Trace elements are elements that are needed for reactions in very, very small quantities. So let's take a look at examples of them. The major ones are the CHOPN, C-H-O-P-N. C, carbon. Major ones are the CHOPN, C-H-O-P-N. C, carbon. H, hydrogen. O, oxygen. P, phosphorus. N, nitrogen. You do not have to write out elemental names. You simply use the elemental symbols. C is carbon, H is hydrogen, O is oxygen, N is nitrogen, P is phosphorus. In that, you may see something that looks like this. The subscripted number next to the elemental symbol tells me how many atoms happen to be there. So in this case here, I have 2 atoms of what? Oxygen. If I combine it with 1 atom of carbon, I now have CO2. Carbon what? Dioxide. If I put a number out here before it, this tells me how many moles of the molecule I have. Simply how much mass of that molecule I have. The minor ones include things like calcium, Ca, potassium, K, sulfur, S, sodium, Na, chloride, Cl, magnesium, Mg, iron, Fe. Without going into all the derivations of stuff, these elemental symbols are based off of the Latin and Greek root terms for the English phrases. So like iron is ferric, Fe. Trace elements include boron, chromium, copper, fluorine, iodine, zinc, and manganese. Trace elements are necessary for metabolic functions. The problem with trace elements is that some of them can become toxic at anything above trace levels. In particular, copper, and chromium. There's a hoopla about another one of these trace elements, and that would be what? Fluorine, in the form of fluoride, which is necessary in order to have healthy what? Teeth. It's one of the reasons why fluoride is added to tap water. When we look at these elements and we look at these molecules, we break them down into their classifications. The big two classifications that we have to look at here is polar and nonpolar. Polar molecules act quasi-magnetic. So they act like a magnet, which means that they will have a positive end and a negative end. Nonpolars do not have that. The positive end and the negative end on a polar molecule has to do with where electrons spend their most amount of time. Because polar molecules have this positive and negative end and nonpolar molecules don't, they don't regularly interact with each other. The most common polar molecule is what? Dihydromonoxide, also known as water. That's the most common polar. The classification that is most common for nonpolar would be what? Most common nonpolar? Lipids, fats. Fats don't interact with water. Go home, fill up a cup of water, go grab a bottle of whatever oil you happen to have in the kitchen, and pour it into the water. And you'll notice, well, it will separate due to density issues. Oils are less dense than water. But you'll also notice where the oil and the water start interacting, the oils do what? They make little balls. The little balls are ensuring that the polar does not interact with the nonpolar. Because of the polar not interacting with the nonpolar, it forms a very distinct feature that is important for biological life. And that would be the formation of what? There's your hint. Membranes. If it wasn't for the nonpolar not interacting with the polar, we would not need membranes. The next thing we have to worry about in terms of classifications is the organic versus the inorganic. Simply put, organics, molecules that have carbon. Inorganic, everything else. Anybody taking OChem? Organic chemistry? Those of you planning on going into medical fields will most likely have to take organic chemistry at some point in time. Organic chemistry is simply looking at elements that have what molecule in it? Carbon. When you took your general chemistry class, most of that dealt with inorganic chemistry. Inorganic chemistry is anything that doesn't have carbon in it. Most of the metabolism that we look at in our body is organic chemistry. Along with the classifications based off of organic, inorganic, polar, and nonpolar is the issue what's referred to as ions. Ions are elements that have either lost an electron or have gained an electron. If it's lost an electron, we give it a special term. An anion. A-N, ion. Anions have a negative charge to it. So the chlorine ion is Cl negative. This means gain an electron. If it's lost an electron, it's called a cation, CAT ion. Common example would be the sodium ion, Na+. All ions typically are seen in what's referred to as a salt formation. And we've all seen this salt before. NaCl, sodium chloride, or table salt. The way in which the elements shed or gain electrons will dictate the way in which they bond or interact with each other. If they share electrons between elements, between atoms, we refer to it as being covalent. If one sheds the electron and the other one accepts the electron, we refer to it as ionic. If we have a polar molecule, we have a separate classification of bonds that can occur. And we'll get to that when we talk about water. And that would be what's referred to as a hydrogen bond. Covalents are the strongest of them. Ionics are the weakest of them. So let's see if we can look at some examples of the various molecules. So, examples of polar molecules. Well, we already talked about water. There are proteins and amino acids that are polar. And there are several types of carbohydrates that are polar. One type of carbohydrate that is a non-polar is sucrose. Sucrose is table sugar. If you pour table sugar into water, the table sugar stays as table sugar until you heat it up and the bonds dissociate and it allows to form a solution. Non-polars, lipids, and there's a whole bunch of different types of lipids. One type of lipids is referred to as the steroids. Another type of lipid would be cholesterol. And then a whole host of amino acids are non-polar. One of the common non-polar ones that are out there is what you can pick up at most of the health food stores. Or if you go to the nutrition aisles of the stores where they sell it, the protein powders, in particular the casein protein, is a non-polar. So you dump it into water and it will just settle. Whereas whey is apolar. You dump it into water and it starts to almost automatically dissolve. In fact, the Little Miss Muffet nursery rhyme, curds and whey. Curds is the fat. Whey is the polar protein. Organics, and we'll get more detail of this. Carbohydrates, lipids, proteins, nucleic acids, and one of the most important one, adenosine triphosphate, which we don't write out as adenosine triphosphate. We simply write what? ATP. ATP makes your body run. If it wasn't for ATP, you wouldn't be able to do anything. The non-organics are things that don't have carbon in it, and for our body, the most important ones, water, and then salts, in particular, sodium chloride, potassium chloride, calcium chloride. We can add a few more. We can add some phosphates in here. calcium phosphate, which we call hydroxyapatite. Calcium phosphate is important. Hydroxyapatite is the principal salt in what tissue? Bone. We can also have floral phosphate, and that's the principal crystal in what tissue? Your teeth. And then ions. Ions are extremely important for physiological functions. It's the ions that establish membrane potentials, and it's the membrane potentials that establish membrane dynamics. Any change in ions around a cell will disrupt how the cell functions. Worst case scenario of ion disruption is where you have the sensation or the phenomenon of a cramp. A cramp occurs because of an ion disruption. And we'll take a look at that when we look at how cell membranes function. Now we'll try to pull up some videos for you to see what happens to people when they actually have cramps. And all the cramping is because of an ion disruption. Questions? Yep.
So lipids are fats.
Yes.
Cholesterol is a fat. So when they say you have high cholesterol, they're saying your fat levels are high.
Okay. When they measure cholesterol in the blood, they're actually measuring what's referred to as a lipoprotein. So schematically, what they're basically doing is there's this vessel in the bloodstream that traps a whole bunch of fat molecules within it. And that's what they're measuring when they look at blood lipid levels. They look at this here and they look at triglycerides within the bloodstream. And so within cholesterol, there's 7 different types, but the 3 principal types are the LDL, the HDL, and then what's referred to as the VLDL. The D stands for density. Density is the relationship between mass and volume. The general atomic mass of all of this is relatively the same. The only thing that's changed is how densely packed everything is together. So when they measure it in the bloodstream, these are what are usually referred. So this is the worst. This is the bad cholesterol. This is the good cholesterol. And the reason why they call it good and bad is because they're lipids, so they don't interact with the water in the blood, and so they float on the top. As they float on the top of the blood, as the blood gets pushed through the vessels, it interacts with the surface of the epithelium of the blood vessels, and it starts adhering. And as it adheres, it triggers an immune response, and the immune response causes what we call atherosclerotic plaques, atherosclerosis, which causes the cardiovascular disease. And so when you do a blood draw and you look at cholesterol levels, this is what they're looking at. When we talk about the cholesterol molecule itself, the cholesterol molecule acts as a membrane stabilizer. And so when we look at the cell membrane later on, probably next week, we'll see it, and we'll actually see where the cholesterol fits in. And what it does is it keeps the cell membrane intact as the cell membrane changes its shape.
So in simpler terms, does it prevent the bloodstream from flowing?
The cholesterol itself does not.
Oh, okay.
It's the inflammation that occurs because the cholesterol is causing damage to the epithelium. Any other questions? Everybody knows where the lab room is?